Welcome to the pre-recording of lecture 29. So this is the first part of our 15th session already, the start of the 6th week in the 8-week summer course. As always, I will have a slide presentation, then a demonstration with the Jupyter notebook. Typically, I try to limit the number of slides that I have, but for this lecture, there are many concepts that I want to explain. So we talk about quality of software, software testing, and how you can reason about programs. In this part of the course, you have already seen many scripts. You have written also a couple of them, and you can reason, and you should be able to have an impression a little bit on when software is correct and not. This is a mathematical computer science course, so there is a link between proving theorems and proving the correctness of programs. So both of them are about ensuring correctness. Correctness being the main property we care about above everything else. So, what is quality? In this course and also within computer science, we look for industrial quality, what we can measure. Um, so, in one sentence, quality is what you expect from a product. Expectations, uh, there has a statistical quality to it, as expected by the user. So this is important. Um, I will try to make this more precise how you can get to having good quality. It's an integrated part of software development, no matter what kind of methodology that you are using. Um, Companies actually often employ as many testers as they have developers. And the beta testing is actually done by testers. So there's also the alpha testing, but that's done by a developer. Um, So software testing is that part of software engineering where one systematically searches for bugs. So I mentioned the spiral model. So there are 4 stages. Just to emphasize where we currently are, we are in the verification stage here. In the spiral model, there are only 4 stages. Briefly, the analysis is concerned with the commitment of the resources. Most likely, do you have time for this? Time equals money. Design is important. So we can design algorithms by flowcharts. We design object-oriented programs via the Unified Modeling Language, UML diagrams, before we begin to the implementation. So it's good to have things drawn out first in the design phase, even if the design is only in your head. So after an implementation comes the verification. If there are problems, then you should first analyze, do I actually have the time and the resources to commit to it? Is there something wrong with the design? So did I actually forget to design a module before you then get to the implementation? In this course, we can work now in pairs. But up to the first 2 computer projects, we've always worked individually, so there's actually not that much difference. With the spiral model, when I first introduced it, I said that we start with a small prototype and then it spirals out to a more complex program. You could also see more that now, actually here now we return to programming in the small, where the spirals actually are converging. So the stages, so if the length of the the length of the arrows is indicating the length of the stage, then you can see that as we do here 3 iterations, the stages actually get shorter and shorter. And at the very end, we converge to one dot where we have a correct program. All right. Here is a motivating anecdote. So it's historically, so the Pentium bug. So this to indicate that software is not only, not only the industry, not only software industry is plagued by problems. Also, hardware makers have problems with often, as in the past, with their chips. So there is this historical problem with the Pentium chip, an earlier version, where there was a division problem. And it was noted by an unexpected result from your calculations. So if you have a software bug, then it may happen that indeed there is a hardware error. But here this was reproducible. What was even worse was that the test engineers actually knew about it. But then the management had decided not to fix it and was not even announced it. So once the bug actually came out, there were attempts to diminish it and say, well, it only occurs. So that was the second mistake. So then they would only replace the chips if you could provide proof that your application was affected. So these are the 3 mistakes that were made as a consequence of making that bug. But then the replacements actually are done. So the replacement actually did happen of every faulty Pentium chip. So now actually, as a standard practice, known bugs are actually uh, announced and actually feedback is actually provided. Okay, what is now a software bug? So first of all, I have to refer again to the specification. So specification relates to what software does, or actually it defines the software. So the specification is written in the design stage. That's why the design is so important. One needs to have a formal document of what the software should do. In this course, every project had a description, and that was specifying what the program that you were supposed to writing was supposed to be doing. There are 5 rules when a software bug occurs. Um, some of the rules are very obvious. So the software doesn't do something and the specification says it should do. So the software is not complete. The software does something and the specification says that it shouldn't be doing this. That's also wrong. The software does something that the specification doesn't mention. So that is something that is an undocumented feature. Um, which is actually also, which is not expected. So this is the unexpected behavior. 4 is typically the hardest to understand because it's a double negative. So the software doesn't do something that the specification doesn't mention, but it should. My example to this is the calculator. If you would buy a calculator, but you would not be able to perform a division, then even if the specification wouldn't mention that there is a division operator, it's still a calculator. So it should perform division. So even if it's not mentioned. Um, so if it does a division, but the specification doesn't mention the division, then that's also a bug. So that's rule 3. But rule 4 is that some software um, should do something, but it doesn't do it and it doesn't mention it. Nevertheless, you expect it. Um, so one can think of other examples, but the calculator without the division is, I think, an obvious. Then the fifth point is actually mainly it's a so the definition from a book I got from a book. I'm not entirely satisfied with it, but point 5 is when nobody actually knows what's going on. So the software is difficult to understand, hard to use, slow, or just not plain right. So there's something wrong with it. So the user perspective is also important here. So in some sense, the bottom line of every slide is important. The user comes in as well. So this is the form an attempt to a formal definition of a software bug with 5 rules. What you need to know from this in the course towards exams, I can give you a rule and then you must give an example. Um, all right, what type of testing do we um, distinguish? So the job of software tester is a very serious job. So it's a job in a software company. So we distinguish between white box testing and black box testing. So with white box testing, the tester knows the internal structure of the program. So if you have, for example, a module, you can see all the functions in the module. And you can actually test each and every function that is offered by one module. So you can test the functionality. Um, so you have the internal structure. With the black box testing, you only see the manual basically. You only see you can read the design. So you see the functional specification. So there is the developer's perspective and there is the user perspective. So being a tester doesn't even often require that you are a coder if you do black box testing. You just need to, well, so you need to have a very good sense of reading documentation and picking out the pieces that are unclear or just not right and starting to test from there. There are very different categories of testing as well. So you can actually, so there's the static testing and there is dynamic. So static means always that nothing moves. So it's just reading, again, just between quotation marks, because really reading for comprehension is hard. Trying to really understand what happened. So you can read the specification or you can read the source code. So I'm using the binary way of working here, but you can see the complexity of testing. So you can look at the code, you can look at the specification statically, but also you can execute the software. That's the dynamic, but you can also do the beta testing, the black box, where you are based off the specification, or if you have access to the source code, you can try to look for the cases that the developers may have overlooked. So some functionality that seems to be missing or seems to be faulty. Okay, going back to the essence now, there is verification and there is validation. So the bottom line on one of the slides was the user, and this is always somehow makes us uneasy as software developers. But verification means that does the software meet the specifications? But software doesn't stand on its own, so it's not just a piece of art where up to contemplation. No, it actually needs to be functional. It needs to be doing what the user requires. So user requirements means is strongly worded. So there is the validation. Um, it's often subtle. It looks often subtle. So in mathematics, you solve equations. You can think about have we solved the equations right? But also have we solved the right equations? So that's the validation perspective. This is very important in mathematical modeling. You can have a mathematical model that perfectly predicts the weather, and you can predict to the last decimal place what the exact temperature will be at any given hour on every given moment in the future. So you can give it with very high accurate precision, but it's actually not at all accurate. So your model is wrong. So another famous example, so you can look this up in Hubble, so the Hubble telescope, it met all its specification on the ground, but not in space. So space is very difficult. That's why they talk about rocket science. So you can actually only know when it works if it is in an entirely different environment. So the environment of the user is often entirely different from the environment of the developer. And I'm, when developing this course, may have made that mistake as well. I have a very nice laptop. Students often have not so nice equipment. Um, so often one needs to be adaptable. That's why the spiral model is so good. So specifications, assuming, don't assume that the specifications are correct. So in the design phase and in the analysis phase, interactions with the user or with people who are familiar with the customers and their expectations is very important. Also, familiarity with similar products. All right, if you work in a pair, then you can work as coder and reviewer. So peer review or buddy review, if you for the next third project, you can work in pairs. So one, if you work in different time zones, one can be the programmer, the other be the reviewer, and the roles may switch. You start with a review, what your buddy has sent you when you wake up in the morning. You review it, and then based on that review, you make changes and you send off to your buddy who will start by reviewing. All right, I will mention Pylint at the very end. There are static analyzers, so a lot of it is practical. But if you look into code, if you are an experienced programmer, you can see what should you check for. If you have a loop, there should be an initialization. Um, Typing is important. For computations, if you are working with floating point numbers, hardware floats, there might be overflow or underflow. Deciding when two floats are zero is often a very tricky problem, so there is a course numerical analysis which deals with this problem. If you see an if test, is there an else? So are all the cases covered? Now note that we can have multiple conditions. Are all these different states covered? Um, in designing a function, we've seen keyword arguments. You can actually force that the user calls a function with keywords arguments. If not, if you don't enforce this, if there's only one argument, that's silly. But if there are many parameters, you may enforce the keyword. So argument because of the uh, possibility of errors with incorrect orders of input. Data is on file. What happens if the file formats that are written by the programs is not really consistent? So are the cases covered? In the next lecture, so the following part, we will see exception handling. Okay, one more type of testing. You can test to pass when you are, as a user, on your best behavior. You have read the instructions, you have understood them, and you are following the instructions. You just don't do whatever you feel you should do. You could also test to fail. You could try to come up with test cases where you know uh, there might be an exception, or you will provoke an exception. Here is a very simple test again for the calculator. You can check, and as a developer, you often check the most basic cases. 1 plus 2, 1 plus 5. Can your calculator do this? But then you have 1 plus 9999999. So in Python, we have arbitrary precision arithmetic. We shouldn't really worry about this with the integers. But nevertheless, if you start working with huge numbers, you should watch your memory consumption. So we test to pass, test to fail. There is also testing on the state. So you test on the data, but you also test on the logic of the program. So especially in a dialogue, so you have all the specific states you can in, are all the states actually covered? Again, with the if else, if what happens is if some tests are not made. So there are decision tables that are important as well. That's why we considered the truth tables. So truth tables are often also a very exhaustive way of testing all possible outcomes of a logic expression. All right. One more type of testing. So unit testing and integration testing. You can test at the module level. So this is again if you have um, access to the source code. If you can test with a module. If you see the source code, you can actually check all the tests on the functions. You can actually run the test function as well. So most modules actually should come with a test that you can run. Um, when you install software, often you have the possibility to run a test, so that we'll see whether all the tests are passing on that component. There is the unit testing and there is the integration testing. So then there are the two approaches also to programming. You have the top-down programming, but then the bottom-up. Um, so bottom-up testing means that all the modules come with test drivers. But if you are working, say, in several teams, then the team that works from the top may not have the modules, but you can actually, with the top down, you can work with stubs. So you can replace um, your instead of having working with sensors, you can work with a file with temperature values. So for the third project, we are working by displaying a pie chart for data. You can test your pie chart on any frequency table. So the two are independent from each other. So on the person who writes the module to compute the frequency table should actually produce the frequency table, the person who writes the visualization can work with a stub. With, say, you should agree first on the data, uh, what the stub should look like. So also here, if you have your file with the test temperature values, you should agree on the ranges of the numbers. So what comes in the test temperature value should within the range what the sensors will give you. Um, so that has to deal also with the consistency of the data that was mentioned earlier. So testing is very complex, and with the binary we can with the binary classification, we can kind of get a control of the complexity. But here you see that there are many types of testing. So there's several testing areas. So there's configuration testing. Often when you design a program, it works very well on Linux. But then the nightmare starts if you have to port it on Windows. Be mindful of that. So also software never exists in a vacuum. Providing a scripting interface to your software, or at least providing a callback function, makes it already quite good that your program will be accessible to other software. When we talked about good design, so the input output is often in a separate module, all the interaction dialogues with users. So if you have to uh, export your program to another language, that you as the developer don't need to go through every line in the software to see where the print statements are. Um, is it easy to use? So it's not because you as a developer are using it that it's easy to use. So be mindful of that. Writing good documentation so is also extremely important. Don't assume that you have a tool. Sphinx is a great tool to write software to document Python code. Knowing how to use the tool is one thing, but knowing how to write good documentation is another point. Okay, so I will not dabble onto this. So I'm already half hour in, so I'm at slide number 15. I read a book that is listed here. So software testing. So the job on a software tester is a very serious job within software engineering. So you see the book is in a second edition. All right, let's now talk more practical. So how can you build um, good software, software that actually satisfies, so where you can prove. So there are two other languages that are mentioned here. There is IFAL, and then there is Ada, Ada 2012. I designed this. It's not the most recent version of the Ada software, but it is a more recent version of Ada. Supports contract-based um, software programming. In Python, we have the assert. The assert can actually enforce preconditions and postconditions. I will give an example of this. There are also loop invariants. So here is an example on how you can add asserts. Now, this is more and more testing, but the advantage of the assert is that it will trigger a hard exception. It will crash your program. But then if you turn on the optimization, it will actually turn off the debugging flag. So you can test on this explicitly with if-else statements, but if you do that, you will add extra complexity to your program. Python can turn the optimizations, can actually turn off these tests. So uh, that's one way to promote the assert statement. I mentioned the loop invariant, so here is the simple example that I will use. So we are enforcing conditions, the preconditions and the postconditions. So we are searching for an item in the list. Uh, it is different from the index in the sense that index will crash when the item is not belonging to the list items. So in a way, it's our searching of the list, which is returning the same as the index, except that it doesn't crash. It gives us a -1. With Python, the -1 is the last element. So that's actually also a valid index to the list. So that's why the Python designers have opted for index to give a value error. In the next lecture, we will see how we could catch that error. So a loop invariant is a property that remains true. So it's a relationship between the variables that remains true during the entire execution of the loop. And you can use that to prove the correctness that you go from the precondition to the postcondition. So you satisfy the postconditions. So preconditions are the conditions on the input parameters. The postconditions are the conditions on the output. And here they are written already more formally. So in languages such as Ada, you can make that formal and actually do have correct software. As a Python programmer, you can also enforce this with the asserts, as I will demonstrate this. Python evolves, so one of the later notations are one of the later versions 3.9 I read, or if I remember, or our current version of Python supports gradual typing. So there is dynamic typing. So the Python interpreter will not enforce them. So assert can be used for that. So Python is very permissive, very flexible. That's why it's suitable for a first programming language. It's very tolerant, and it's also a high productivity language. A statically typed language forces you to determine the type of each variable. So static means not executing. So the type of every variable is fixed. This makes it the programmer has to be a lot more disciplined. So here are two examples of annotations. So you can in some sense by when you use a new variable, so I'm here using name, and I can insert the type of the variable. It's a string. Now you can later assign to name an integer or float. Python will permit it, no problem. But with the annotations attributes, you can actually check what it is supposed to be. So you can write an assert that whatever you do with the name, that it's really what was intended when the name was declared. So this is very similar to a static type declaration in a statically compiled language. Python also supports that you provide the type of the input parameters. So with our search items, so we are looking for an item that is an integer and the lists here. So it should be in list and it should be checked that the integer is part and then return the index. When you do help search, you will actually see that type information. So that's the syntax in the newest edition of Python. All right. To conclude, so what's the use to mathematics? So what is also the relationship between the verification of the correctness of programs and the proving of theorems? So some theorems, some theorems are very easily stated. So if you have a map, you will need no more than 4 colors to make sure that any pair of two adjacent countries, they have a different color. or formulated no two adjacent regions receive the same color. Very plainly stated, conjectured in 1852 and only proven in 1976. So more than 100 years later. So this is to indicate how hard and how frustrating mathematics can often be. The proof was a computer proof. In some sense, people have also conjectured that most interesting proofs will no longer be checkable by humans in the end. And there are proof assistants. If you formalize your proofs, then you can actually have mathematical software that produces the proofs for you. So that's the connection between the formal verification of mathematical proofs and the formal analysis of computer programs. All right, who was Grace Hopper? I had the picture of John von Neumann and his machine. Grace Hopper is also very um, um, famous in the development. And there is the anecdotal origin of the word bug. Write a paragraph is the first exercise to explain in your own words the question. Um, Pylant does static analysis, it also rates your code and it provides meaningful suggestions. In some sense, in the next second half of this lecture, we will go into exception handling. At this point in the course, you may have had already lots of frustrations and seen many error messages from the Python interpreter. At this point in time, you should be able to make sense of them. Pylant will also give you suggestions. Run Pylant. If you look to the former computer projects, if you had bugs, explain the bugs. Many of the computer programs in the previous lectures were kind of intended to go to more larger programs. For example, the polynomials in one variable that was covered in the previous lecture was very much incomplete. Perhaps I admit many scripts that are posted at this course website have many bugs in them. But they are useful for pedagogical use. The search item. I will introduce a float. I will present a flow chart again. Writing the specification of a sum of list of integer numbers, there is the sum, but you should be capable of writing a formal specification in terms of pre and post conditions. And you can actually then also use the assert to make a more rigorous implementation of the sum, satisfying the pre and the post conditions. Okay. I'm almost spent the entire lecture on the slides because there's so much to say about this. I will briefly scroll through Jupyter Notebook to emphasize what it all means for us Python programmers. So here you see the Jupyter Notebook that has several sections in them. Jupyter Notebook is very good to illustrate what you would otherwise type in the Python shell, and I can document. So the assert is a Python construction. It's also available in a language such as C and C++. So you can assert a property. So here I have, assert takes on input any logical expression. If it evaluates to false, like here is the case, you will have the assertion error. So the assertion error causes when the debug mode is true, and that's the default. Now in your script, and that would be an extra exercise, put these two statements in a Python script and run them. with Python, just Python, and you will see the assertion error for this third statement. Run this with the Python -o, and that's an optimization, and your program should not crash. Try this exercise. So preconditions, postconditions, and loop invariants. So I give again the definitions. So precondition is often formulated as the type. So often what happens is that the developer of a function expected that the user would provide an input argument of a certain type, but that didn't happen. So the function was misused in some sense. The function crashed or provided some wrong results. So precondition is actually also for you as a software developer who writes software for others, kind of to ensure that, hey, we have the correct on values on input. It's also another way to guarantee the communication between modules. It's kind of an act of defensive coding. A post condition is also a formal way to announce to your user what to expect of the output. So in some sense, the user can actually take the post conditions and see whether they match from the preconditions in the next function. So I will focus here on programming in the small, but you see if every function in your module has the correct precondition and postcondition, that you can do some automated testing. So seeing where in the chain of functions, so we see a program often as a sequence of data transformation, where in that chain there was a problem. So you can think of logical expressions. So this is why the truth tables were so important when we introduced them with the branching conditions. So you can formally start to write up. So we will see the example I will give is search item, which searches an item in the list. So it's there are two arguments, list items and an integer item. Notice that we have seen that Python is object oriented and that every name of a variable is an instance of some class. So as a programmer, we can actually use the is instance to check it. So you can check it with an explicit if test and then write an error message, but that's often a little bit cumbersome. You can do this with an assert. The output specification, the number that is returned is an integer. It's either -1 or it is the index. And here you see that I have already very specifically written down in logical expressions that can be evaluated by Python. They can be the input argument to the assert. So let me again look at the algorithm. So I made this algorithm with a flowchart. So I will post it. So here you see the diagram environment. So there are the two diamonds that are sitting in there for the two tests. We have two variables, the pos for the position, that is what will be returned. By default, if never an assignment is made to the position, it returns -1. The index is the index of the item if it is found. So here you see the two tests. Flowcharts define the algorithm after better than in code. So making a flowchart is, if you like, it's actually part of the design descriptions of the before you start to do the actual implementation. They are important if you start to modify. So we have the dot index, the index method, but the motivation here would be that we want to write our own version of it. It's silly if it is on a list, but you will deal with composite data structures that you design on your own. So you may want to have that way where the index is replaced by the memory location in the identification number of the object that you can dereference for the position then. All right, so here is now the function. So you see the documentation string, which was earlier on one of the slides. And then you see the assert using the instance here. So I can use the assert as a function, but here it is used assert, still assert without the function. So with the notation as before. So the assert can be used as a function as I did before. The assert can also be used without the brackets. So both are fine. So Python is extremely permissive often. Assert item not in items. So you can see it actually is quite readable. There is the slicing of the items. So each time we take a bigger slice and each time we actually run the in operator. So if you are worried about complexity, this is a quadratic cost. So we will see more about complexity and cost later on. So testing could be costly as well. So that's another aspect why testing is often not feasible. So this will be extremely prohibitive if you are dealing with huge data sets. I should mention that. So I want to illustrate the loop invariant, and it's important that even if you don't do formal program analysis, is that you can read code and that during the execution of the code, if you are inside the body of the loop, you have the condition. So we have the initialization as well. So the initialization test might actually not be true, but if it when we have an empty list, but if it is true, then actually that's actually the first part of the loop. So when the loop runs in the body of the loop, we will actually have two statements. The the current index is still less than the total length, and up to the items before, so the index, if you slice, it's also the previous index. It's not yet in there. So we will return the first index where we have the match. If the loop terminates, then it means that either these two are wrong, either you are at the end of the list and you haven't found the item. And this is when the position has not been changed. You never executed the if statement. You never broke out of the loop. It's only when you have a quality here that you have broken out of the loop. And you see when the loop invariant becomes false because you jump out or you break out of the loop, that then the post condition is satisfied. So in some sense, this comes very close to a formal verification of the correctness of the loop. We have a list, so every list has an index, so we can index with an integer. So the index here, I didn't use the annotations yet. So I also having that I'm looking for an integer. Okay, so I could have added the annotations, so they are fairly recent. So I just illustrate again how you can work with them. So here, this would be the short presentation for the search. So if you had to implement this in Python, you know that there is the dot index, but the dot index will fail if the item is not in the list. It will trigger an error. So you actually don't want, you want that -1 is returned. So this is an implementation that comes to satisfy our restrictions. And then there is Pylint. One of the exercises is to install Pylint. I will demonstrate this. And actually here you see, perhaps I should leave this up. So here you see that that Pylint gives me um, the score. So typically I actually try that my script has a perfect Pylint score. That does not mean that my software is correct, by no means, but it means that I'm following the recommended style. And this is a dynamic evolving language. Some of the older style guides are no longer applying, but I try to adhere to it. You can see the use of the assert. So let me see the previous version. Let me scroll down. So here you see I had unnecessary parentheses. It gives the line number, and then there is an unnecessary else after the break. So here you see the search, here you see the code. I had actually an else. I was thinking every if must have an else, but if you have a break, then actually you will never execute this. And I now agree that after if your if statement contains a break or a return, if you exit the loop, then if the if is true, there is never an else. So that's a superfluous else. And static code analysis actually detects this. So Python is actually extremely good. It will actually also detect bugs uh, before you run them, and it may actually give you a hint why it is wrong. So this is actually quite powerful. So Pylint is a very good tool to use and is recommended. Okay, I'm running out of time. Um, I hope this lecture was interesting. So there is a lot to say about correctness of software. Um, I will stop here. In the next lecture, in the second half of the session, we will introduce exception handling.